The issue is that these three requirements that, again, naively you think I want all three, are incompatible. Simply because a finite continuous range has infinitely many points, and if you want additivity, well, something's gotta give, right? And this is exactly what happens in the third case, in the discrete classical mechanics, continuous quantum mechanics, and quantum mechanics. All these three sacrifice one of those three requirements. In this video, I'm going to present some idea that we developed in a paper that we recently published, which I leave a link in the description. The general idea is to extend the notion of count of states that you have in classical statistical mechanics to quantum mechanics, and the hope is that this actually can give us a new way to understand the theory and actually to understand exactly what quantization is. At least I think that's something that comes out of this. And this is sort of the general idea of a research program that we're starting right now, because there are essentially open problems in mathematics that we actually see here that needs to be solved, and not being a mathematician, not working on those things, are things that I'll have to figure out how to solve. So let's get started. The main result is that, again, if we want to extend this notion of quantum states to quantum mechanics, so that we can do quantum probability and quantum information theory in a way that is similar to what we do in classical mechanics, then we need a novel approach to measure theory. We need essentially non-additive measures. So what I'm going to do in this presentation is go through the idea of why we think this is even a reasonable thing to look at. Actually, kind of surprised that this wasn't done already, because as you see, sort of the equation, what we're actually doing is pretty straightforward. And then see sort of the preliminary result what we have, and then discuss some of the consequence of trying to do this. So first of all, why we're going to trying to do that? Well, because we really think, as part of our research project program Assumptions of Physics, that we really need to fully understand what the mathematical structure we use in physics represent. So the idea that the way that we see mathematics and its relationship to physics is that in physics we develop models of physical systems, and the formal part, right, the mathematical part, starts with essentially a bunch of formal definitions that are there to capture something in the physical world. So it's important to understand what these definitions map to the physical world, and why, and show that the things in the physical world actually have the properties that the mathematical structure is there to capture. So just to give you an idea of past result, we have shown that topologies in Sigma algebra correspond to experimentally verifiable statement and statements associated with experimental tests. So the idea that this part of mathematics is there in physical theory to capture the requirement of experimental verifiability, and everything else that we use in physics actually is built on top of those structures. So it makes sense that in physics we would require those structures for everything. We have found a set of necessary and sufficient assumptions to model a physical quantity as a real number. And again, here are the papers, but you can find the sort of the better and more formal work done in our open access book, Assumptions of Physics, which is available on our website. And from the physics side, going more from the higher level structure, we have a reverse engineer the action principle, so that we have geometrical and physical, more than interpretation, way to rederive the action principle, so that we know exactly what the Lagrangian and the action is, and why you must have the principle of least action. And also we have a sort of a complete reverse engineering of Hamiltonian mechanics to show that it's is the deterministic and reversible evolution of frame invariant distribution. So we have a lot of stuff done very, very well in quantum mechanics, where I feel all warm and snuggly about it. But in quantum mechanics, there's still some things that are not quite as nice as we're able to do them in quantum mechanics, because we don't have this complete parallel. So what we're really missing here, if you understand the mathematical stack, these are the topological part are really the low level, and the action principle and the Hamiltonian mechanics are really the higher level differential geometric structure. Well, there is the part in the middle that is the measure theoretic structure. That's the part that we really are missing to understand exactly what's going on there, and this is the part that we're starting exploring in this project. So if we look at, again, how classical mechanics work, because we have a full idea of how classical mechanics work, one of the important thing that we found is that the geometric, the probabilistic, and the information theoretic structure are really the same structure, in the sense that you can't give me one without giving me the other. And this is how it works. The geometry of a phase space, of classical mechanics, of position and momentum, in mathematics is described by symplectic geometry. And within that symplectic geometry, we have a definition of volume, which is this mu of u. If I give you a set u, you're able to tell me how big the volume is. And this is called the Liouville measure. And this plays a crucial role in the definition and the description of classical mechanics. Now, if we want to put probabilities over a phase space, and we want to, for example, characterize a uniform distribution over a set U, what's going to happen is that the probability density is really going to be the inverse of the measure of the volume. That way, when you reintegrate this, you're basically going to multiply by the volume, and you're going to get the total probability as well. And note that, again, this is just an inverse, so this is an invertible relationship between the measure and the probability. So if I gave you all different probability distribution in terms of points without giving you the measure, you would be able to recover the measure by taking the uniform distribution over a set, look at the probability density, and do the inverse and recover the volume. Right, so there's, in this sense, the structure are the same structure. You could argue that we have the volume so that we can define the probability densities, or you can argue that we have the probability densities so that we can define the volume. It's the same thing. The other part is information theory, and in information theory what you have is the Shannon or Gibbs entropy, the Gibbs entropy for the continuum, which is the sort of continuous version of the Shannon entropy that is actually the one correct for classical mechanics. Again, if you apply the entropy over a uniform distribution, what you find is that that entropy is going to be the logarithm of the volume. Right, so that's, again, the logarithm is an invertible function, so if I gave you the set of all possible probability distribution without even giving you the densities, but just giving you the entropy from each other, you would be able to determine, oh, these two density actually have the same support, and this is the one that is maximal, or the one that is maximal is going to be the one that is going to correspond to the uniform distribution, and the uniform distribution is logarithm of measure, so you're going to be able to recover the measure itself. So again, the point of all of this is that there is really this one-to-one map between the structure. You can go from one to the other and recover the other. So it's really, mathematically, it's really conceptually one structure. And again, the Liouville measure plays a crucial role, because the Liouville measure counts the state in a region U. What the symplectic form does is that it allows you to count the configuration for each independent degree of freedom. So it's not that different. And the important thing is that the phase space, again, the idea of position and conjugate momentum, is the only type of manifold in which the count of state, this Liouville measure, is frame invariant. So it's the same for everybody. And that's how we recover classical mechanics, is basically say, okay, we have this manifold for our states, and we want to have a probability distribution, entropy, determinism, reversibility in a way that it's coordinate invariant, and then you say, okay, that manifold must be a symplectic manifold, you must have a Liouville measure, and so on. So this is all perfectly understood for classical mechanics, and now we want to do something similar for quantum mechanics, because we want to understand quantum mechanics as well as we understand classical mechanics. So Again, in quantum mechanics, we are going to have three structures. One is the geometrical one, which is given by the projective Hilbert spaces. And this geometrical structure is determined by the inner product. If I give you two states which are going to be represented by the rays in the Hilbert space, you're going to be able to have an inner product, and that inner product determines the geometrical structure of the space. And then, of course, we have some kind of probabilistic structure, and we have the link for the Born rule that the probability of transition is equal to the square of the inner product. And again, this is something that you can go one-to-one. Again, there is sort of a little underdetermination here, because the probability does not determine the inner product, does not determine the phases, but that's exactly the structure that the projective Hilbert space does not care. The Hilbert space care about these absolute phases, the projective Hilbert space does not, and so again you have this map that is one-to-one. And again, in quantum mechanics, we also have information theory. And again, we can do something similar as we did before. We can take two states and create the uniform distribution between two states and go and calculate the entropy using the von Neumann entropy, which is the correct entropy for quantum mechanics. And you find that this entropy is actually equal to the Shannon entropy, the one that we use in discrete, with these two coefficients. Again, it doesn't really matter how this works. The point is that this is also an invertible function. So if I gave you the set of all possible uniform distributions among two states, and I would give you the entropy of all these things, you would be able to recover the probability, and therefore you're going to be able to recover the inner product, therefore you're going to be able to recover the whole structure of the Hilbert space. So again, this means that there is really one structure. All these three things are conceptually really the same structure, the different aspects of the same structure. And so this makes our job easier, because if we find one way to understand this whole structure, then we can basically understand the whole thing. Now, this is a structure that is very different from the one we were before, and what you can see is that there is no measure theory used here. There is really none. There is these Hilbert spaces. Of course, there's going to be some measure underneath to define some things, but really the geometrical structure is not in terms of some differential form in the same way that it was done in the other way. And what is really missing from all of this is really there is no way to count state. We don't have a measure that you give it a set of states and that tells you, oh, these are the number of states that are correct for those states, in the same way that we have in classical mechanics. And so the idea is that we saw that in classical mechanics the Liouville's measure, the count of states, is so important that it basically sort of defines the whole thing. Can we introduce a quantum analog for that? And maybe it's going to turn out that that thing, in the same way, is going to tell us exactly why we have the structure of quantum mechanics, and is going to give us, again, a little bit more insight of why and how we have the thing that we have in quantum mechanics. So it's basically the general idea. But first of all, before going through the details, it's probably better that I tell you a little bit what measure theory is, because on the physics side, people probably don't have an idea of what measure theory is. They might think that it's connected to measurement. Not at all. It's just a measure theory is just a mathematical name, like open set, that there's nothing open in a sort of open close in a book kind of way or a door kind of way. This is just a mathematical term, so we need to understand what it is. And but on the other side, we also need to understand how it's applied to physics, how we use it in physics. So just knowing the mathematical definition is not enough. So that's exactly what we need to do. We need to understand what it is, what measure theory is, why do we have it, and how do we use it in physics. So let's start with something that you would probably have as a naive way to think of, let's say, probability. The naive way that people think of probability is the one that they probably get from combinatoric, is that there is a set with a possible set of outcomes. So if I have a six-faced die, I'm going to have six outcomes, 1, 2, 3, 4, 5. And you assign the probability to any of these outcomes. So if the die is balanced, then it's 1/6 for all of them. And then you have a set, and a set corresponds to an event. So for example, if I say that the result of the die is going to be even, that corresponds to the set of cases 2, 4, 6. And so if I want to know what's the probability that the die is even, that's going to be the set of cases, and just going to sum the probability all of them. So it's going to be 1, 6, 1, 6, 1, 6, which makes a half. And this is the general idea, that the naive way that people think about probability. The issue is that this does not work on the continuum. And a way that you can see it is that suppose you want to have a uniform distribution between 0 and 1. Now you have the problem that there are infinitely many points, right? And so if you assign a probability that is finite to all the points, then the probability on the whole range is going to be infinite. And if you want to assign a probability that is finite over the whole range and it's the same for everything, then the probability for each point basically goes to 0. And measure theory is really there to design, is designed to solve this problem. And the extremely cool thing is that then with this definition, you can essentially treat the discrete problem and the continuous problem in pretty much the same way with the same definition. So you have a more general set of definitions that work a lot better. And so what are these definitions? Well, it is to assign a measure. The measure assigns the number not to the point, but to each subset. So the measure, the value of the measure could be a size, could be a probability, we'll see that later, right? But really the idea is that the measure is a function from a collection of subsets, not on points. This collection of subsets is special, it's called the sigma algebra, and it has the property that is closed under complement and countable union and countable intersection. And this is the correct closure for experimental tests. This is a result from a previous research. So really you should think about the sigma algebra as assigning a value to an experimental test. And so if you're assigning probability, it's going to be the probability that the experimental test is positive. If you have a volume, is the size of the volume in which you're performing the test, and so on. And now if you define the probability in this way, now the probability, what you're going to have is that the probability for a uniform distribution between 0 and 1, if you take the set between 0 and 1, the probability is going to be 1. If you take the subset from 0 to 1/2, then it's just 1/2, and so on. So the idea is that this is giving a lot more information, because it's not just giving you the points, but also giving you the sets. So there is more information, but this information is highly redundant, because there is an assumption of countable additivity. So like before, if we have a set, we can go and look at points. Well, this sort of generalizes that. If we have a set and we can break that set into a set of a collection of disjoint subsets, then the probability of the whole is the sum of the probability of the parts. And so this is in a nutshell what measure theory is. It's just a function that I give you a set, it gives you a number, and it's countably additive. That's it. So how do we use measure theory in physics? Well, there are essentially two ways. One is what we said before, probability measure. Probability measure is a measure, and one of the main features of the probability measure is that it's bounded to 1, in the sense that the probability of the whole set is 1, right? Something's gonna happen, and that's it. 150% probability does not exist. Now, the quantifying measure is another thing that we do, which is kind of what we were talking about before of the Liouville measure. We are trying to count the number of states that are in phase space. And this measure can be infinite, because if we take the infinite range of position and the infinite range of momentum, then of course we have infinitely many possible states, right? So, and the measure is actually literally infinite. It's not tends to infinity as we had before, right? The range of the value of the measure actually includes infinity. The measure has to be defined on every subset. And we have quantifying measure not just for a number of states. We might have quantifying measure for initial condition, measurement outcome, and then when we essentially define meters and units on continuous variables, really what we're defining it's measure. those are the things that we're defining. That's why that there is this name of measures that sort of comes with the idea that we're trying to measure, for example, the length of an interval by measuring it in meters. But then it's sort of not quite the same thing, because, you know, it's not the same when we're talking about probability of quantum states. But that's where the name comes from. One of the things that we're going to do over and over is take a ratio of measure, especially ratios of probability towards quantified measures. And we're going to take this ratio because really we are interested in probability per state, probability per initial condition. And again, since we have now this general framework, that we can think about these things generally. If we have a set U and we take the probability of having something in that set, and the count of how many things are there in that set, then we can just define P of U over mu of U, and this will give you the average probability per state. And then the idea is that if we take that set U and we make it smaller and smaller and smaller until we get to only one element, then we are going to get the probability for that particular state. And this object that we can define in general is going to be slightly different depending on whether we are in a discrete space or a continuous space. So how does it work? Well, in the discrete case, the counting measure is really the cardinality of the sets. How many points are there? And so if we're going to take this limit, and when we're going to have U corresponding to a single point, we are going to have the counting measure over a single point, which is 1. And therefore, this will actually correspond to the actual probability that you have for that particular point. Now, if you are in a continuous case, then we are going to use a Lebesgue measure, which is basically the sum of the interval. If you imagine that you have a real line, the set U, you can imagine a set of disjoint interval. You just sum the length of all the internet. That corresponds to the Lebesgue measure. And again, you're going to be able to take this limit of the probability over that Lebesgue measure. And now what happens is that when you are going to go and take the limit, the measure for that particular point is going to be 0, because the interval is going to have 0 length. But also the probability is going to become smaller and smaller and smaller. And so what you're going to be able to define is the probability density. And this is one way to define derivative. This is the one that we use in measure theory, and it's called the radon-Nikodym derivative. And to me is actually the definition of derivative that makes the most sense in physical terms, because whatever we measure in physics is always about finite size objects. And so this is capturing that you're making the ratio of finite size objects. Okay, so this is how it works. Again, note though that there is an issue, is that the Lebesgue measure depends on the unit. As I was saying before, this measure can be meters, time, Kelvin, whatever. Any continuous quantities will have a unit. And so in principle, these measures are not frame invariant. Every observer will have their own set of measures because they have their own set of measurement scale and reference system, so on. And again, the important thing is here that phase space fixes this. The Liouville measure, the volume in phase space, is actually frame invariant. It's the space is there such that sets count of states are the same for me and the same for you, so that the physics that we create is objective. And this is really the important things, the thing that the Liouville measure solves. So again, this is the discrete case of classical mechanics. This is the continuous case in classical mechanics. And how does this work in quantum mechanics? And again, you probably know that quantum mechanics is not really a classical probability theory, but we actually use classical probability theory a lot. And one things where a lot of people get confused, and by people I mean even professional people, physicists that work on this stuff, is that we use classical probability on preparation and on measurements, but not on states. So the classical probability that we use on preparation and on measurement, the measure that we use actually depends on what type of thing we're describing. So if the observable is discrete, for example, we have discrete energy level of a harmonic oscillator or an isolated atom, then the measure is discrete. And if the observable is continuous, like position and momentum, then the measure is the Lebesgue measure in that case. And so what the way that we use these things mathematically is that if we have a mixed state, right, this mixed state, we have, let's say, a classical uncertainty on the possible preparation. So we have all these psi x correspond to all the possible preparation. This rho of x is a classical uncertainty, is a probability density on the preparation. Now this object is classical, and then we do this integration, and it turns out that we can actually do this integration correctly, because on the space of pure preparation there is actually a measure that is the measure that we can use on preparation, and that's also a symplectic Louisville, so it's a frame invariant. Voila, it's very good. And then we get this object, and this is the quantum density matrix. This is the quantum object, right? And so this part here is classical, and we can go from a classical probability distribution to a quantum state, quantum mixed state. And this object here is not classical at all. It has very non-classical features. But this object here that we're doing, then that part is classical. Same thing when we do have a density matrix and we take probability out for probability of measurement, this probability is going to be a classical measure. And how does it work? You basically have an operator for each subset that corresponds to the k that you are measuring in your possible k outputs of your detector, and what you get here is that you're going to have the probability of associated with this kth result that is going to correspond also to a set of possible states, and this measure here, and this measure here is a classical measure, because the probability that we get from our measurement, they are classical measure. So the thing that we cannot do instead is assign a measure, assign a classical probability distribution on the states themselves. That's the thing that we can't do. This is what people want to do over and over, and it cannot work. So in quantum mechanics, you're going to have a probability of getting the kth result of a measurement given some preparation and given some measurement apparatus. And this can be calculated, as we saw here, is the trace of the density matrix corresponding to the preparation, which you can calculate here, and this operator that corresponds to the measurement and the kth outcome of the measurement, right? This works, and this is purely quantum. What people would like to do is to take the preparation, say that the preparation prepares a state, like some kind of ontological state, and then you take that state, and that state is what determines the outcome of the measurement and the probability of getting it. This is the part that you can't do. You can't take this and split it into two. Why? Well, again, because if you wanted to do this, you need a measure here for the integration. You need a way to count the states, these ontic states, these quantum states, and that's precisely the thing that quantum mechanics does not give you. And even if you were able to do this, this object here cannot combine with the rule of classical probability. So if you have a mixture of preparation, right, something that here you're using with classical probability, and you're doing some type of operation here using classical probability, you can't do that here. You really can't. Things are just going to break up, and then you're going to not be able to get all the feature that quantum mechanics has. Okay, so we said that it cannot work, but meaning that we cannot do it with the standard measure theory, with the tools of classical probability. So can actually be done with some other tools, and if we were able to do it, how would we do it? Of course, I don't have the answer for all this, but if we were able to do it, the first thing that we need is the ability to put a measure on the set of states of quantum mechanics, and an ability to count state in quantum mechanics. And this is the question: what would be a reasonable way, a way that makes sense for the quantumness of the quantum mechanics to count quantum states? So let's first go back to classical mechanics and again refresh how this is done in classical mechanics. So as we said before, we have a uniform distribution over a set U. and this set might be discrete or continuous, and then we would use the appropriate version of entropy, the Shannon for the discrete system and the Gibbs entropy for phase space. And then if the distribution is uniform, we would find that the expression for the entropy is simply the logarithm of the count of state. And this expression is so important, the fact that the entropy is the logarithm of the count of state can be the starting point of the formulation of classical statistical mechanics. That's is called the fundamental postulate of statistical mechanics. So of course, something like this does not really exist for quantum states. But in quantum statistical mechanics, there is a related expression. And if we take the entropy of a distribution over a set of states, and again, the entropy has to be the von Neumann entropy because that's the correct expression for quantum mechanics, you find that this is less or equal to the logarithm of the dimension of the subspace spanned by the set U, right? And this expression is going to have an equal if you have a uniform distribution over the span. So again, it's not exactly the same thing that we had before, but it's pretty darn close. Like, it looks very similar. So again, one would say, maybe we should extend the previous expression for quantum statistical mechanics as well. Well, there is another way to look at this by looking at information theory. And information theory links the number of possible messages to entropy in this way. What you're going to have is a distribution for a message source, and for any distribution of the message source, and again, depending if it's discrete, classical, continuous, classical, or quantum mechanics, you have to use the appropriate entropy. But the interesting thing is that the output of this calculation, this n, always have the same meaning, and it's the average number of bits per message that you have to use to transfer the information from the source. Very cool. And of course, there is a simple expression from a number of bits to message, a number of messages encodable in the bits, which is 2 to the n, because every bit is going to give you 2 combinations. So if you have n bits, you have all the possible permutation, and that's just 2 to the n, 2n times. Now, you can imagine that if you have a uniform distribution and you are imagining to use one state for each possible message, then this number corresponds to the number of states. And so it makes sense that if you have a uniform distribution, the entropy of the uniform distribution is going to be the logarithm of the number of possible messages, which is actually the number of possible states. And so again, this sort of justifies the extension of this relationship to the quantum states. If we wanted to define a count of states in quantum mechanics, and we wanted it to make sense, we basically need to be something similar to this. Otherwise, it just doesn't make sense. Okay, so we can use this as a definition, right? As I said, in classical statistical mechanics, you start with the count of states and then you define entropy as the logarithm of the count of states. Here we're going to do the opposite. In quantum mechanics, we don't have the count of states, but we have defined an entropy for uniform distribution, and we use that to define the count of states. And we see what we get. Are we going to get something that makes sense, or are we going to get something that is totally meaningless? Let's find out. Let's calculate what happens for measures of sets of 1 and 2 points. And again, we are just going to look at a two-dimensional subspace because we have 2 points anyway, so they're going to live in a two-dimensional subspace. And the two-dimensional subspace is the Bloch sphere, so every state in a two-dimensional system is a point on the surface of the sphere. And now we just, so we're basically trying to put a measure-like thing on the surface of the sphere, and we calculate it by creating a uniform distribution of 1 and 2 states. So if we want to calculate the count of states for a single pure state, this is going to be 2 to the entropy of a uniform distribution over one state, which just means it's the pure state. But the entropy of a pure state in quantum mechanics is always 0, so we have 2 to the 0, and so this is 1. So the count of states for a set with only one state has measure 1, which is good, makes sense. At least this part makes sense. Now we have to imagine of calculating the measure for 2 states. And for 2 states, we're going to have 2 to the entropy of a uniform distribution of 2 states. So a mixed state where you're doing a 50-50% mixture of 2 states. Now this gives us a little bit a more complicated expression, this minus 1 plus square root of p over 2 logarithm of 1 plus square root of p over 2 minus 1 minus p and so on. You can read it. The point is that this expression here, however complicated it may seem, is a number that goes from 0 to 1. And it's 0 when these two states coincide, and of course, which is good because we get this first case. And it's 1 if the two states are orthogonal in the Hilbert space, but in the projective space on the Bloch sphere, orthogonal actually means they are opposite from each other. And this would correspond to states that can be the outcome of a single projective measurement. And so what happens is that the entropy of the count of states of 2, then, it's going to be bounded by 2, and it's going to be 2 if the states are orthogonal. But if the states are not orthogonal, so I have this and this there, for example, we have spin up and spin left, then that measure is going to be less than 2. It's not going to be additive. Okay? So we have something interesting here, is that that sort of makes sense. First of all, each state counts as 1, and we recover additivity only when we have, say, spin up and spin down. We have outcomes of the same measurement. All the states are in the same context. And when you have measurements that are in the same context, that's exactly where we would expect to get classical probability, because that's what we get out when we are doing a measurement. We do get classical probability. So this actually makes a lot of sense. And when you don't have states in the same context, as in you have a spin up and spin right or spin left, then those things, the measure that we have there, the count of states there, is not additive, signaling that there is something weird going on. And again, if you recall the original thing that we said, we saw that the geometry and probability information theory are equivalent, and they were derivable from the entropy of uniform distribution between two states. Well, this is what this measure is giving you. So if you have this measure, you're going to be able to recover the inner product and everything else. So all quantum effects, in principle, in some way that I don't see, but mathematically it tells me that they should be linked to this non-additivity of the measure. So the point is that if we can find some reason then for this non-additivity of the measure, maybe this is going to tell us why there are these quantum effects and why we must have these strange things. So that's the first thing that we have to understand. Is the non-additivity that we saw that it's not that we have when we are not in the same measurement context, does it make sense physically? Can we find a physical justification, right? And so what we really have to show is why do spin up and spin down correspond to two cases, but spin up and spin right correspond to fewer than two cases. What does that mean anyway? So the insight here is that the state of a system is never completely independent from the environment. So you need a specific environment to have a specific state. Therefore, when I tell you something about the state, I'm going to tell you something about the environment. So for example, if I tell you there is a cat inside a box, then I'm implicitly telling you that the box is not on the surface of the sun. Because if it were on the surface of the sun at 5,000 Kelvin, whatever temperature there is there, the box would not exist and the cat wouldn't be there. So the statement there is a cat inside a box would not be applicable, would be totally false. And the same applies in a much more sort of practical experimental sense to quantum states. So if I'm preparing a spin in a particular direction or measuring things in a particular direction, I'm implying that there are some boundary conditions because I've chosen a preparation setup or a measurement setup that is specific for that orientation, right? I have oriented some magnetic field or some polarimeter. I have done something to my measurement or preparing apparatus that has decided that's the direction that I'm going to work on. That's the thing that I'm going to do. So if I told you, oh, I measured spin up or I measured spin right, well, I told you something about the setting of the measurement device. So that there is this link. And so really the spin up and the spin right, the spins, the states that are not in the same context, they are not two cases at all else being equal. It's not like spin up and spin down. I've changed nothing of my measuring apparatus. There are these two possible cases, and these two cases are completely independent from the environment, and therefore there really are two cases. The spin up and spin right instead, they're not in that condition. And so the idea is that contextuality should interact in some way with the count of states. That makes sense. Of course, what I don't know is why exactly this particular way. Could we derive and really define what is this correlation with the environment and then say, oh, of course, like this is the way that you must count things? That I still don't know, but at least we can see that there must be a link between contextuality and non-additive measure. That sort of makes total sense and it's totally physically justifiable. So now that we've seen that this non-additivity does make sense, let's compare actually all these measures from the discrete, the continuous, and the quantum case. And we're lucky that we can do that because again, we saw that the two-dimensional case in quantum mechanics, a two-state system, is a Bloch sphere, is a sphere, so we're putting a measure on the surface of the sphere. Well, the state in classical mechanics for angular momentum, for example, can also be a sphere, and of course the discrete measure we can put it to any state. So we can actually apply these different measures on the same space on a sphere, right? So we correspond to three completely different physical cases, but mathematically we can do it so that we can actually compare the mathematical properties of these things. And so the first thing that we want to compare is how the measure, what does the measure give us for a single point. So if we have a classical discrete case, then we have a counting measure, 1 point, cardinality 1, then the measure is 1. In the quantum case, we also saw that the entropy was 0, and therefore the measure was 1. So these two agree. But for the classical continuous, right, a point, the volume of a point is 0. Therefore, the count of state is technically 0 for a single point. A point counts as 0. It's like it's not really there. Now, if you imagine a finite continuous region, for example, the whole sphere, right? Now, what's going to happen is that the sphere is going to have infinitely many points, and therefore the cardinality of the whole sphere in terms of the classical discrete measure is going to be infinite. So we have infinitely many states, infinitely many points. For the classical continuous instead, like we would have the surface of the sphere, and that's a finite value. So for the finite continuous region, the classical continuous case gives us a finite value. But what happens is that's exactly what happens in quantum mechanics. If you remember when I said that there was this bound that was given by the dimensionality of the span of the states, well, that's exactly it. So if we put a uniform distribution over the full sphere in quantum mechanics, we get the maximally mixed state, but the maximally mixed state can also be achieved with a 50-50% mixture of spin up and spin down. So taking a preparation where you have complete uncertainty over the direction of spin, or taking a preparation where you know that you prepare spin up, but you don't know if you prepare spin up and spin down. Those things in classical mechanics, they're exactly the same thing. And that's why quantum statistical mechanics is completely different from classical statistical mechanics. This means that if we take this the surface of the sphere, again, that state corresponds to a 50% spin up and 50% spin down, which is the measure of two opposite orthogonal states, which means we have calculated before, the measure is 2, which is finite. So the classical continuums and a quantum agree on giving finite measure for a finite continuous region, where the classical discrete is different. And then of course we have additivity, and we saw the classical discrete and classical diffusion are additive, but the quantum is not additive. And I find that this is really very interesting. Why is it interesting? Because if you didn't know anything and you say, okay, I want to create a measure that counts state, you would naively think that you want these 3 requirements. You want single points to count as a single case, right? So a point in space, yeah, that should count as 1. It's one possible configuration. Then you would like a finite range to be finite, because a finite range, 1 meter, carries finite information. And so you would like the measure on a finite continuous range to be finite. And you would want the measure to be additive. If you have a disjoint set, the measure of the whole, the number of cases on the whole, is the sum of the number of cases of the parts. The issue is that these 3 requirements that, again, naively you think I want all 3, are incompatible. Simply because a finite continuous range has infinitely many points, and if you want additivity, well, something's gotta give, right? And this is exactly what happens in the 3 cases, in the discrete classical mechanics, continuous quantum mechanics, and quantum mechanics. All these 3 sacrifice one of those 3 requirements. The discrete classical mechanics sacrifice requirements number 2. The continuum classical mechanics sacrifices the first one, points at measure 0, and quantum mechanics sacrifices the additivity. And this also gives us some kind of insight of what is actually being quantized here, right? The quantization is a weird word, because if you ask what exactly is quantization, well, it's like this really ad hoc mathematical procedure where you get some sort of classical state and you substitute some things formally and you get some other structure. And you do it in a formal way. There is really no physical reason why you're doing that. It just works. So it's never really clear, and it was never clear to me, what is actually is that you're quantizing. Because if you think about it, the energy level are quantized for one system, but not for the other. They are quantized if you're bounded, if the system is bound to something else. If it's free, they're not quantized. So it's not really the values that they are quantized. And so what is it that the quantization is doing? Well, what is actually being quantized is the count of states. We are basically taking something that is continuous, right? Where the measure would go to 0, and the entropy would go to minus infinity, and we say no, the state cannot be a single state cannot count less than 1. That does not make any sense. So we put a lower limit on the measure for state, such that each state count 1, and we still have finite measure on finite regions, because that makes sense. And then, of course, we sacrifice additivity. So that, to me, is really what this quantization procedure is doing. And then, of course, what I don't know, is this the only way that this can be done? I kind of have a sense that probably it is true, that's the only way that it can be done. But again, having a hunch is not being able to prove it mathematically, and this is kind of the thing that I like to be able to do if I can, because you can never predict whether you can actually do these things or not. But at least I think this, at least to me, gives a really interesting insight of what actually quantization is doing. It's putting a lower limit to the count of states, and that makes a lot of sense to me. So to wrap up, then, quantization is really fixing the quantified measure so that it's bounded from below, so that each states count to 1, and this comes at a price, and the price is non-additivity. And this is what makes the probability and measure theory non-classical. It makes it such that we have a lot of these weird things that we can't recover from classical probability, because classical probability is additive. And this also implies contextuality. Some states cannot be prepared and all else being equal. So basically, in a nutshell, I think this is what this whole investigation tells us. So now you might say, okay, well, this is very fine and nice, but what can I do with it? I already have quantum mechanics, so why should I stay there and think about with this quantized measure and so on? Well, I think this is important because I do believe that quantization of space-time most likely will require some sort of quantized measure like that, right? So when we went to classical mechanics and quantum mechanics, the whole mathematical world had to change to accommodate this very weird requirement. And the idea is that very likely something as math breaking is going to happen when we go to a field theory, to a quantum field theory, to really a quantization of to a field theory that lives in a quantized space. And again, what I really want to have always is really good physical motivation for the math and knowing what exactly we were doing. So we were able to say, okay, quantization is putting a quantized measure on the number of states, because we do want that each state counts 1. So what does quantization of space-time actually mean? Because if I do not know even what it means, how can I even know what are the mathematical requirements that go inside there, and whether the current mathematical tools that we have are actually enough or not? So let's start with the observation that in a field theory, we have one independent degree of freedom for each point. So in a field theory, the full state is described by a field, and the field is everywhere. So I'm going to have one point here, I have one value here, I have one point here, and I have a value here, and so on. So we have one value for each of the point, and technically the value at each point is independent from the other. I can put whatever value I want here and whatever value I want here. The choice here, it's the same of the choice here. And now what happens then is that, again, we need to be able to count these degrees of freedom, and the idea is that the volume, the space-time volume, actually the spatial volume, counts this independent degree of freedom in a region, right? If I have this region, I'm going to have some degrees of freedom. If I chop the region in two, well, I would expect again a measure that the number of degrees of freedom on the left side plus the number of degrees of freedom on the right side gives the total number of degrees of freedom. Right? There's a sort of an additivity that we are imagining on having, and the space volume should be, as a physical thing, telling us how many states, how many possible configurations are there, and therefore how many degrees of freedom. And again, if we're using the standard measure that we have for volumes, which is the volume elements that we have for Riemannian mechanics, for Riemannian geometry, we have some sort of Lebesgue measure that again, it will give us regions with measures less than 1, because the whole thing is additive, and you divide in half and half and half, you're gonna take, the measure is gonna be half and half and half, and therefore you're gonna keep having the number of independent degrees of freedom. And then at some point, you're gonna reach a volume that has less than 1 degree of freedom. And of course, that does not make sense in the same way that saying that we have a region of phase space where we have less than 1 state. right? That's exactly where classical mechanics, classical statistical mechanics break down, because it starts giving you negative entropy. And this similar is going to break down because it's not going to make so much sense. And so the idea is that if we really wanted to have space-time quantization, then what we are actually doing physically, very likely, is that we want to quantize the count of degrees of freedom. And we are going to have similar problems than what we have for the count of states, right? The region is going to decrease and decrease, and then at some point it's not going to decrease as fast. It's going to converge to one. And again, this physically would make sense because what the measure counts is independent degree of freedom. And if degrees of freedom are very close, they're at Planck scale, then we would expect those degrees of freedom to not be independent, and therefore if we have 2 degrees of freedom that are independent, they would be like orthogonal, like in the quantum case, they would count at 2. But if the 2 degrees of freedom are dependent, they are, there is a correlation between them, then we wouldn't expect those to count as 2 as the one that are independent. So I really think that quantization at a logical sense, at a conceptual sense, it's this problem that we need to solve. And most likely we will need some technique that are like this. We need some sort of integration and a measure theory that works with these quantized measures that are highly non-additive and non-monotonic and so on. So that's basically it. That's sort of, as I said, I don't have all the answers. This is just a way to look at things, and I think it makes a lot of sense. Like a lot of sense, because it kind of tells you why we have these things. I'm still surprised that this hasn't been looked at. I looked in the literature. I talked to people that know the literature, the historical literature better than me. Nobody was able to tell me, oh yeah, this is something that so and so has done. And it's very strange because really almost everything has been done in quantum mechanics. So anyway, so this is the type of thing that I think we should be able to investigate, and if you can help, I wouldn't mind. So these are the type of questions that are there in my mind that to be frank, I don't even know exactly how to answer. One thing is that counting and Lebesgue measure are in some sense unique, right? The counting measure, for example, you just need to tell me the value for the single point, and when you say that the point is 1, then you're fully defined. But you could say that the point is 2, or that 1 point is 1 and 1 point is 2. So you could do something weird there. But in any case, in some sense, the counting and the Lebesgue measure are unique. And now the question is the quantized measure unique? Is there some sense that, if I have a sphere and I want this non-additive measure that has some certain feature, well, I need to recover that, and I will have to recover the von Neumann entropy and so on. And the other question in that is that does wanting a quantized measure constrain the type of space like the frame invariance on the counter state does in classical mechanics, that we are able to recover the symplectic and position momentum time space, or there is another way to do quantization. There is another space that may be physical. Who knows? If it's physical, then if there is another way and it's physical, then it's good. Otherwise, it means that we don't have the correct starting points. But this is an open question to me. Is there another way to do that thing or not? So does essentially this notion of a quantized measure already is enough to say, oh yeah, you gotta get quantum mechanics, or not? There are other possible ways that either are physical or need to be described. So in general, if I want to have a quantified measure on states, what are the most general requirements that I have to put on that? Clearly additivity is not one of them. But what are others? I doubt that it can be just any measures however you want. So for example, in quantum mechanics, there are still some consistency requirements between sets of 2 and sets of 3 elements. I just don't know what they are. What are exactly what are they exactly? I know that, as I said before, from the entropy of uniform distribution on two states, you can recover the whole thing. So you would know how to calculate it on three elements and so on. So there must be some, consistency requires between these things. I don't know what they are. I know that the entropy, for example, has to be strictly concave, and the measure of entropy is linked to the measure of quantum state. How does that concavity transfer there? I have no idea. Good questions. I don't know. How does it work for composite system? In composite system, you would have the product of the Liouville measures in classical mechanics. How does it work for quantum mechanics? I have no idea. That's a whole thing that needs to be studied. And again, the idea is, can we put a quantized measure on a Riemannian space so that we could have some idea of how to quantize space-time with this motivation. And we do have a link between symplectic geometry and Riemannian geometry, so maybe that's a venue to pursue this, maybe not. I have no idea. And can we define a theory of integration over these non-additive measure so that we can define probability distribution directly over states? This is basically the real mathematical question that is way outside of my capability in mathematics, and so I'm trying to find mathematicians to help me, but I always get a feeling that I'll have to figure it out by myself. So the main sticking point here is that there are books and work on non-additive measures and theory integration based on non-additive measure, but they are typically based on monotone measures. The idea you make the set bigger, and then the measure can only increase and or stay the same. And the quantized measure is actually not monotone. Like if you add points to a set, the measure can decrease. So for example, if you have unequal mixtures of up and down, that's the maximally mixed state, that's entropy 1, therefore the count of states is 2, and now you add a third point, so you do an equal mixture of up, down, and right, and now at that point you do not have the maximally mixed state anymore, the entropy decreases, therefore the count of states decreases, and I don't know whether this is going to break up everything. There might be sub-additivity, I don't know. So there's a whole thing that needs to be studied there, and from the look at the literature that I've done, these type of things don't seem to have been looked at, so there might be new math that needs to be developed. So if you're a mathematician and want to help me, please contact me, because I don't know whether I can do this by myself. But anyway, so that's sort of the ideas that we have put out in the paper, and we actually got a grant from the John Templeton Foundation to work on these things. So thank you for paying a part of my salary and for allowing me to go and tell everybody these crazy ideas that I have. And I hope you find this type of ideas as insightful as I do. And I guess if you want to know more, you can look at the article that again is going to be in the link, and look forward to future videos, hopefully where I have figured out the answer to this question. So for now, thank you for your time, and see you next time.